Hello everyone, I am Rahi, and today as part of the final project for Mind 5025 I'm going to present about the frictional stability of faults and the concept of rate and state friction. So before we actually understand what exactly is rate and state friction, we have to understand how a fault fails in a generalized theory. So as people from the rock mechanics community, everyone knows what Mohr-Coulomb failure is. So Mohr-Coulomb failure is, let's say if you look at this diagram on the left, you have a block of rock and there is a fault which passes through at an angle theta. You're injecting fluids via a borehole which affects this fault over here, and the state of stress on the fault changes. And this fault will change the moment the shear stress developed in the fault due to this stress perturbation caused by fluid injections falls down below the shear strength of the rock according to this Mohr-Coulomb envelope given on the lower bottom side. And on the right you can see I have drawn Mohr circles. So the black Mohr circle is the initial condition, and sigma 1 and sigma 3 are the vertical and horizontal normal principal stresses, and due to pore pressure injection there is a del P change in the normal stress which results in this whole Mohr circle to shift towards the left and become this red Mohr circle over here, wherein the effective vertical principal stress is sigma 1 prime and the effective horizontal principal stress is sigma prime 3. And now you can see that this Mohr circle is touching the failure envelope, which means that this fault begins to slide. It fails. However, this theory just tells us that when the fault is going to fail, what is the stress condition which will lead to failure, but does not go into the intricacies and the micromechanics of the physics behind the process that is going on. It does not say how the fault is going to fail, and in general does not say anything about if that failure of fault is going to cause any kind of seismic activity or earthquakes. So we will use the concept of rate and state friction to understand how earthquakes are formed, and we will show that Mohr-Coulomb theory is a very simplistic understanding of the failure of a fault and will not do sufficient justice to the actual mechanics of earthquakes which is going on in the background. And we need to understand what is going on, and we need to look at the history of the research in earthquake mechanics in general and see how the concept of dynamic evolution of friction was kind of developed by scientists over the decades, and how that led into the formulation of the concept called rate and state friction, which is a widely used empirical physics-based relationship to understand the nucleation of earthquakes. So, to understand rate and state friction, let's look at the assumptions made by Mohr-Coulomb theory. So Mohr-Coulomb theory just says that failure is controlled by the instantaneous stress at that point, and that the friction is actually constant, and the moment the friction is exceeded, the fault fails. It assumes that the fault surfaces don't heal, compact, or do not evolve with time, and as soon as the failure point is reached, it just fails. And it also assumes that the fault material is homogeneous and isotropic, and it ignores any kind of heterogeneity, localized weakening zones, and roughness patches in the fault. It just assumes that it is a surface wherein the stress state results in its failure. But in reality, with physics and all the observations that have been done in experimental research and in general observations in nature, we know that surfaces are always slipping, even if it's an infinitesimally very small value, but they are always slipping. And that has been observed in experiments as well. So on the right, you will see this picture was taken from a paper by one of our collaborators, Surat Anakul, and was published in a Nature Communications paper in 2025, wherein he conducted some experiments on something called the PMMA block, which is a polymethyl methylacrylate. It's kind of a fiber. So there is a fracture plane which goes right through the block, and some stresses are applied, and they observed for a long time, they observed that if you keep the surface just as it is, it's going to slip at a very, very tiny velocities as shown by this plot. You can see that the slip rate is very, very small, but it's not zero. It gradually goes down towards zero, but as it tries to achieve steady state, it's still not zero. It's still always slipping. and that is the reality for any kind of material in the world. So if we try to compare Moore-Coulomb with the concept of earthquake nucleation, you see Moore-Coulomb always say that if a surface is going to slip or not slip. But earthquake nucleation theories say if a surface which is always slipping, will it creep or will it go towards an unsteady state slip? So creeping means it's going to slip at a very, very, very tiny velocities, and will in theory will not cause any seismic activity. That's called as steady state creep. An unsteady state slip is when the fault just runs away. Fault completely goes away at infinite velocity with its earthquake nucleation. And we will try to understand how stress perturbations causes a system like a fault to change from steady state creep domain to an unsteady state slip situation. And we will also understand how the evolution of friction due to these stress perturbations with time changes the condition of the fault from a steady state creep to unsteady state slip. So what happens to friction? That is the underlying question. So let's try to focus on the underlying questions that will be outlined in this lecture. Why do some fault patches creep while others nucleate earthquakes? What is the physics behind it? That is the main question. Static Moore-Coulomb theory just does not explain when slip becomes unstable. It just explains what stress conditions will result in a fault to fail. So scientists were requiring to formulate a constitutive law linking friction to slip rate and to instability of faults. And people have been working on this for decades now. And one scientist named James Dietrich did some revolutionary work in trying to understand the physics behind the earthquake mechanics by conducting some very simple frictional experiments. And we will look into it. So to understand rate and state friction and what it is exactly and the physical significance of it, we will go back about 4 decades from now and go back all the way to 1979, where James Dietrich conducted some experiments at the United States Geological Survey. So what he did, he took a spring block system, as you can see in the picture over here, and he conducted two different types of experiments on it. He named them these rock friction experiments. So these 2 different types of experiments, one of them was a velocity stepping experiment wherein he imposed progressively increasing slip rates on this spring block system, wherein it means that it progressively increased the velocities of slip of the block spring system. And the other one was a hold slide experiment, wherein he slipped the block for a bit and then held it for a bit, then slipped it again and held it for a bit, and so on. He conducted these experiments in a direct shear configuration on a sample called granodiorite, which is a very hard rock found in Southern California. And he applied a normal stress of 6 megapascals and maintained that normal stress to conduct these experiments. And he saw that how friction is changing with these 2 types of conditions he imposed. So this paper is known as Modeling Rock Friction 1, which is a seminal paper in the field of earthquake mechanics. We will see what are the results of the experiments in the following slides. So the experimental observations of his experiments are given over here. So the first set of experiments, which was basically velocity stepping experiments, as shown in the top left. So you see that friction is kind of steady, and then when you jump the slip rate or the velocity, suddenly the friction jumps, then gradually drops down and then stabilizes, and then he changes the velocity again and the friction jumps again and stabilizes. So you see, friction kind of has a dependence on the velocity being imposed on the block. And this is the top plot is the experimental data which he had, and the bottom plot is an empirical model which he formulated, which tries to replicate the observations of the experiment. And this empirical model is given by these 2 sets of equations below, and he tried to fit these equations onto that experimental observation. And over here in these equations, the parameters C1, C2, C3, F1, F3, these are all calibration constants. So if you do a best fit curve to the experimental data, you will find the values of these calibration constants. So you see there are a bunch of free parameters over here, But nevertheless, the empirical model does a really good job of trying to model the friction evolution with slip rate. Also, this equation over here, where T is d sub c divided by the slip rate times d sub c times slip rate divided by d sub c times t0 exponent of slip rate at steady state minus slip rate divided by d sub c. This equation over here is called the characteristic relaxation time, or basically the time it took for friction once it has jumped to a higher value at a step increase of slip rate to relax down to a steady value. So it's known as here Dietrich named it as a characteristic relaxation time. So these were the results of his first set of experiments, which was velocity stepping. The second set of experiments which he conducted, which were the whole slide experiments, the results of it is given on the right side. So over here he saw that when he imposed a certain slip rate, the friction went up and then behaved a bit weirdly, and when he held it constant, when he stopped slipping body and held it stationary, the friction dropped down. And then when he again imposed another slip rate, it jumped up again and repeated the same behavior for subsequent whole slide patterns. And then he used the same empirical set of equations to model it, and he saw that when he held a constant slip rate, friction eventually it was quite high and then gradually died down and became stable or steady. And when he held the block and then slid it again, all of a sudden friction jumped again and exhibited a similar behavior. And you see over here this d sub c, or the characteristic distance over here, is the time it took for friction to die down to a steady value. And in the caption over here you can see all the free parameter values that were generated by doing a best fit curve. So the empirical model does a really well job and tells us how friction is dependent on the velocity or slip history. This is a very important term that we should remember for subsequent slides. Slip history. Friction is a function of the history of slip. So based on these observations, James Dietrich formulated that the friction evolution of a surface is dependent on the slip, or v function of t, the rate of slip, and also the state of the surface, which is encoded within a variable named that theta t. So friction evolution is a function of rate and state, and thus this formulation is called rate and state friction. And after doing some mathematical assumptions and basic calculations, he reformulated his empirical relation as this function, where friction, which is represented by Ft, is equal to the reference friction, which is a calibration constant, plus A log the slip rate divided by the steady state slip rate, plus B log the steady state slip rate times theta t divided by drs. drs is same as the characteristic distance dc, as you saw in the previous slides. This equation over here is known as the rate and state friction theory. And so over here we need to clear up some terms. Theta is called the state variable. So state variable is kind of ambiguous, but state variable encodes the state of the surface. So when you're sliding a body, the surfaces are rough, they're not smooth exactly. So as you're sliding it, the surfaces they shear and they break and then form again, and those asperities on the surface, they keep on changing with time. And it's very difficult to exactly characterize what is happening, but the state variable theta t kind of does an approximate job of helping us understand what is happening to the surface on a broader term. So we term this variable as the state variable, but it is still difficult to physically constrain this. But nevertheless, we would just go on with the flow and just assume that the work done by researchers like Andy Reina in 1983, where he proposed the aging law for the state variable, these formulations hold true in most cases. So we see that the rate of change of state variable is given by this equation over here. d theta by dt is equal to 1 minus vt times theta t by drs. This is known as the aging law, or what is happening to the surface as it is being slipped or sheared, you could say. And over here on the right, she gives you a good understanding of the empirical relation of rate and state friction. So initially the friction is at a reference value, and with time, all of a sudden you change your velocity from reference velocity v star to v1, and friction jumps to a higher value. This is called the direct effect. And then gradually over the characteristic time t and a characteristic distance drs, it goes to another steady value which is not the same as its initial value. This change is named as the evolution effect. And this is what is happening to any kind of surfaces, all the way ranging from a spring slider model, which is simple, to complex faults in crustal rocks. So you probably wonder that, okay, we know how friction is evolving with time and everything, but how does it help us? I mean, how can you apply this concept to a real-world scenario? So in 1983, Andy Ruina did something called the instability analysis using James Dietrich's rate and state friction theory, and tried to understand how rate and state friction could help us understand the stability of faults and what is impacting those stability. So to understand this, we will do a problem. So this is one of the problems that we're supposed to do as part of our project. So there's a very basic mathematical analysis based on linear it's called a linear instability analysis. It's based on some very basic, determinant and Taylor series analysis sort of stuff, but we'll see what it does. So we assume that the shear stress is equal to K times U minus delta. So we're basically balancing forces over here. Here delta is the slip which has happened in a short period of time. U is the initial position or displacement you could see, and K is the characteristic stiffness. So you can assume that I'm talking about a spring slider model over here, and K is the stiffness of the spring. So U is nothing but the slip rate times the time. U equals to Vt, and the slip is the reference slip rate, which was the slip rate at time 0, or the initial slip rate times the time. And if you take a derivative of it, you will get that del tau by del t is equal to K times V minus V star. And the shear stress, we can express it as tau equals sigma times F, which is a function of theta, and V. So F is an arbitrary function which is a function of variables theta and the slip rate. So based on this, we can reformulate the rate and state friction law as this equation given over here, where tau equals tau star plus A times ln V by V star plus B ln V star theta by dc. So in steady state, del theta by del t is equals to 0, which means that the surface is not changing anymore. This assumption gives us that at steady state, the V star variable is equal to dc by theta star, where dc is the characteristic distance that it takes for a surface to go to a steady frictional value after a jump in slip rate, and theta star is the reference theta, or the condition of the body at the initial time. So now we assume that based on these conditions, a perturbation or a change is introduced into the system, which is of the form as given over here: V equals V star times 1 plus V cap, and this also causes a change on the surface conditions of the body, and that is encoded by theta equals theta star times 1 plus theta cap. And now we use these two equations and we linearize the rate and state formulation for shear stress using a very simple Taylor series expansion and eliminating all the nonlinear terms and considering only the linear terms. We do this both for the rate and state friction formulation and also for Andy Ruina's aging law. And we are rendered by these two equations over here, where the tau linearized is equal to tau star plus A V by V star minus 1 plus B theta by theta star minus 1, and del theta by del t is equals to minus V by V star minus 1 plus theta by theta star minus 1. These last two equations have been generated from Taylor series expansion and then taking only the linear terms. So hence linear instability analysis. Okay. What next? So now that we have the linearized forms of our rate and state friction and our state variable evolution, we do some basic calculations and come up with this term over here, where the rate of change of shear stress is equal to minus k v star times v cap. So we take a derivative of the linearized formulation of rate and state friction and theta, and that renders us with this partial differential equation over here: a del v cap by del t plus b del theta cap by del t is equals minus k v star v cap. And we assume time dependent perturbations for slip rate and the state variable also of these exponential forms over here, and then we substitute them into this partial differential equation, which renders these first two set of equations on the right. So these system of equations can be represented in matrix form as given over here, and for this set of equations to have a solution, the inverse of the first matrix should vanish, which implies that the determinant of this first matrix is equal to 0. We do that. We calculate the determinant of this first matrix over here and set it as 0, and we are rendered with this last set of equation over here, a quadratic equation. So in this quadratic equation, the term beta is equals to b by a, and these b by a are the same parameters in rate and state friction equation, and k cap is equal to the stiffness k times the characteristic distance dc divided by b minus a. Then we divide both sides by b minus a, which renders this second set of equation over here. And then if we substitute k cap equals to 1 into the equation, which gives the critical stiffness of the spring slider system, and this critical stiffness is given by this equation over here. K critical is equal to b minus a by dc. So when k star approaches 0, the equation has positive roots. When k star approaches infinity, the equation has negative roots. When k star reaches a threshold value of 1, the roots become imaginary. Thus we chose that k star equals to 1, which determines the critical stiffness of the system. If our system goes below the critical stiffness as given by k critical over here, it goes to infinite velocity and goes to failure, which means earthquake nucleates. But if our stiffness is above the critical stiffness, which means that it's a stable sliding process, but nevertheless it is still sliding. So the value of the k critical parameter is being controlled by these b and a parameters over here. And based on observations, it has been seen that if a minus b is more than 0, that's a stable creep or slow slip. And if a minus b is less than 0, that's velocity weakening regime, which can nucleate earthquakes. These assumptions are extremely important to our understanding of rate and state friction. However, we must also note the fact that the exact physical meaning of a and b parameters are still not very well known, and it is a huge part of experimental research about understanding what exactly are the a minus b parameters. And also about a major part of my PhD, the experimental part of it would be to investigate what are these a minus b parameters and try to physically constrain them. However, you can see now how rate and state friction is being used to understand the critical stability of a system, and that is extremely important. So basically, what has been seen from observations, experiments, is that these a minus b are dependent on the stresses and the surface roughnesses, and as you are changing the in situ stress conditions, these a minus b parameters change, and that changes the stiffness of the system, and which might go below the critical value and cause earthquakes. Hence, it is very important. So this is what we can do, in terms of understanding the stability of faults using rate and state friction. However, there are so many assumptions over here, and trying to understand this in the context of field scale observations is very difficult. So you might wonder, okay, we do this, but what is a realistic application of rate and state friction which could be applied out there in the field and actually help us know what is going on with regards to earthquakes and understand the physics behind it in a broader scale? we have to understand the concept of seismicity rate, which is much more easier, I would say, to constrain. At the same time, gives much more better information with regards to the inherent stress dependence on seismicity. So instability analysis tells you one thing about the stiffness of the system. However, seismicity rate is more broadly used in modern days to understand how stresses are changing the potential for causing earthquakes in nucleate. So now we will go how rate and state friction is being applied towards understanding of seismicity rate. So we'll we'll talk about understanding seismicity rate forecasting based on a constant stressing history. So James Dietrich then again in 1994 proposed a constitutive framework to get the rate of earthquake production from a given applied stressing history. So stressing history means that the fault is being experiencing the same kind of stress for a long time, hence a stressing history. So basically he wanted to forecast aftershocks that were happening due to a given stressing history following a main shock. And his assumptions were, he considered a volume of Earth having an arbitrary number of nucleation sources, and all sources are above steady state and ready to go, which means that all sources are ready to nucleate earthquakes. So the limitations of this model were that it forecasts aftershocks only, and it only assumes a constant normal stress and a constant shear background stressing. However, he did a lot of calculations and a lot of mathematical modeling work, and he bridged the gaps between statistical seismology and geomechanics to formulate these constitutive formulations over here, where seismicity rate R is equal to the background seismicity rate small r divided by gamma times the shear stressing rate. Over here, gamma is the state variable considered by Dietrich, which is equal to gamma naught plus T by A sigma. Over here, gamma naught is the reference value of state variable. And in his options was that the background stressing rate is constant and the normal stress is also constant. However, you see again, over here this gamma value is unconstrained. I mean, there is no physical significance to it in here, which is very difficult. Nevertheless, if we just consider an arbitrary value for it and we look at what is the forecast given by this constitutive formulation, look at the plots on the right. So these plots show the evolution of seismicity rate using the Dietrich 1994 rate and state model. So the first plot is the effect of initial state variable gamma naught. So assuming different values of gamma naught, you can see as you're increasing the values progressively, the initial seismicity rate drops and then follows a characteristic Omori decay. If you look at the effect of the rate and state parameter A sigma, and okay, I should highlight one thing over here. This big A over here is the same A as in the rate and state friction parameter, where it was represented by the small a, and we call it the rate and state parameter A sigma. So for progressively increasing values of A sigma, we can see that the Omori decay kind of dies down. So with a very low value of A sigma, the Omori decay is quite high, and for a very low value and very high value of A sigma, Omori decay is kind of just dying out. We look at the effect of the stressing rate tau r dot, and this stressing rate is basically the driving force behind seismicity. So we see over here that the impacts of different values of stressing rate and how it changes the seismicity rate. And we also look at how the response of seismicity to stress changes. So if you increase the stress, you see it follows a red curve where there is a quite a very profound Omori decay. But if there is a stress decrease, as indicated by the blue line, the Omori decay kind of fades away. So the Dietrich 1994 model very nicely is able to show how these different parameters impact on aftershock, and very nicely can show can physically constrain the meaning behind characteristic Omori decay of earthquake aftershocks. However, the assumptions of this model is that he assumed that he only wanted to forecast aftershocks, and this model is only valid for a constant normal stress. Normal stress is not changing. So he assumes that each of these population of faults in his 3D Earth volume, which are ready to go, each of these population once and they're all above steady state. He assumes that, and each of these under a constant background stressing rate produces a characteristic Omori decay in seismicity rate. And that the normal stress is not time varying, and you will have like different seismicity rate types with different normal stress step changes, but it's not valid for a time varying or spatially varying time varying normal stress, which is the case which you can see in scenarios of geothermal energy production or carbon dioxide sequestration or oil and gas, where pore pressure changes are causing stress perturbations, or overall changing the stress scenario in the region, and causing like a very profound effect on the overall stress regime in the region. But the Dietrich 1994 model doesn't very well capture that. It just assumes that at a particular stress, your source, earthquake source, would follow this type of characteristic Omori decay. That's what it does. So this model is not enough to understand earthquakes in context of induced seismicity, which is the main focus of my PhD research. So we have to to understand the limitations of the Dietrich 94 model, it assumes a constant normal stress, so a large delta sigma is not handled very accurately. It uses something called a no helium approximation, which fails when faults spend time below steady state. So it assumes that all the faults are above steady state and ready to go, which is not the case in reality. Some faults are dormant, some are not. So we have to formulate a better constitutive formulation to understand that fact. And he assumes that all of these sources are independent, and it neglects any kind of interactions between them. It requires a constant background stressing rate, which is not valid in stress shadows or variable loading. And it uses an abstract formulation called a state variable, which has no direct physical meaning. And the way he constrained this state variable is using this partial differential equation over here, which he formulated based on some extensive mathematical calculations and assumptions. So the Dietrich 94 model fails for complicated stressing histories, and we need to modify and update that and find a more meaningful formulation. So in order to modify the Dietrich model, Hymissen and Segel in 2018 proposed the modified Dietrich formulation, wherein they went ahead and relaxed some of the assumptions of Dietrich and came up with a much more physically meaningful formulation of the 1994 Dietrich model. So in this new formulation, the time to instability that it takes for a source to nucleate is used instead of the gamma state variable, which is very abstract. So gamma is not needed, it is completely eliminated in this case. And the most important part is this formulation is valid for an arbitrary stressing history wherein the normal stress is changing with time. It's a function of time. And it gives very nice integral formulations which are easy to calculate. So you can get like exact solutions instead of a step change in values as in the Dietrich model. And it also gives us a very good understanding of the characteristic Omori decay, and they say that Omori decay only happens for sources which are above steady state. So we will try to understand the formulation of this work using this the block diagram workflow over here. So Hymissen and Segel in this paper, they assumed that again a spring slider model, applied rate and state friction over there, assumed an arbitrary stressing history, and assumed that all the faults are above steady state also over here. They derive an equation for the time to instability, which is basically the time it takes for a source to nucleate, And he extends this formulation into a population of sources, randomly oriented sources in a volume, and construct the evolution of number of events with time, and they derive integral expressions for seismicity rate and compare with how the Dietrich 1994 model performs without the gamma ODE formulation. They also do some other additional work, such as for non-constant background seismicity rate and shear and normal stressing and Coulomb approximations, and they also develop the generalized constitutive formulation. However, that is a bit difficult for to understand, and it's beyond the scope of this lecture, but we will see what they have done over here. So they use the rate and state formulation and do a momentum balance, as over here you can see the shear stress, which is time varying, minus the stiffness of the system times the slip, is equal to the rate and state formulation over here. And then you have your aging law by Arena. So they integrate the aging law and they come up with this integral formulation over here for theta t, wherein theta t is shown by this equation over here, and wherein this ft is this function over here. So for a source above steady state, there is something called a no healing limit mentioned in a paper by Dietrich in 1992, wherein the theta t takes of this form. Theta t is equal to theta naught times e to the power ft. And using this formulation, we assume that, not assume, but we know that the slip rate delta dot is equal to d delta by dt. And we use this formulation for no healing limit for theta t, and we substitute these into the rate and state friction formulation, and we get this equation over here. Kt dt is equal to this big term over here, wherein this kt term is something called an integral stress kernel, which is a function of the time varying shear stress and the time varying normal stress. And this integral kernel will help us see how seismicity rate evolves with the changing stressing history. So tau is applied shear stress on the fault. K delta represents the shear stress drop caused by slip. A and B are the rate and state constitutive parameters controlling the dependence of friction on slip speed and state. V star is the reference steady state slip speed. DC is the characteristic slip distance. Mu is the reference friction coefficient, such that when the slip rate is equal to the reference velocity and the theta is equal to the characteristic distance divided by reference velocity, the friction law assumes a form that tau minus k delta divided by sigma is equal to mu, the friction coefficient. The momentum balance used here does not consider the inertial terms and only applies when slip speeds are very, very low and any kind of elastodynamic effects can be eliminated. So using the formulation for the stress kernel over here, we again use one of the assumptions from Dietrich to simplify this term within the stress kernel. K by A sigma naught minus B by A D sub C is equal to minus H by A. And using this, we reformulate, we calculate, we solve for slip rate and the slip rate as given by these two equations on the left. And the slip rate now is equal to the reference slip rate times the stress kernel KT divided by 1 minus H times the reference slip rate divided by A times the stress kernel integrated over time. Over here, we define another, we see how the time to instability is being used over here. So in this formulation, one of the assumptions is that if you integrate the stress kernel from 0 to time to instability, it renders this form: A by H times your reference slip rate. And this formulation has been highlighted in the Hymes and Siegel paper, and they also show how this has been calculated. So in this equation over here, if you add in the stress kernel as shown in the previous slide, the and if you use this into the slip rate equation over here, you see in the slip rate the denominator is over here 1 minus H times reference slip rate divided by A times the stress kernel integrated over time, Over here, if the denominator goes to 0, then your slip rate goes to infinity, which means, as I said before, earthquake nucleates. It goes to infinite speed. This is called a singularity, and at infinite speed earthquakes nucleate, and thus you get this formulation, and that time in that case becomes a time to instability. Hence the stress kernel integrated with time from 0 to time to instability assumes a formulation of A by H times the reference slip rate. So the time, we can see that the time to instability is controlled by the entire stressing history of the fault by the stress kernel KT, and not just instantaneous stress as assumed by Dietrich in 1994, and is also dependent on the state of the fault initially. So further going down, we applied this time to instability for a single source to a bunch of sources, just like Dietrich did. We assume a constant normal stress and a shear stressing rate which changes with the equation given over here. Tau T is equal to the reference shear stress plus the shear stressing rate times time. And the time to instability now assumes this formulation over here, A sigma naught by the shear stressing rate times log the shear stressing rate by H reference slip rate and initial normal stress plus 1. So the time to instability for the nth source would be T equals N by R, where R is the background seismicity rate. That's obvious. And the previous formulation for the stress kernel now assumes this formulation over here, and thus we can equate this to the stress kernel integrated over time and solve for N, which is the cumulative number of earthquakes. So N by R is equal to TA log 1 by T sub A, and the stress kernel integrated from 0 to T plus 1, where TA is equal to A sigma naught by the background stressing rate. And if you remember, this is the characteristic Maury decay time from Dietrich 1994. Now we take a derivative of N, where capital R is dN by dt, which is the seismicity rate that we observe, which gives us the seismicity rate formulation as an exact solution for an arbitrary stressing history as shown by the stress kernel over here. So you can see over here that for different values of the ratio del sigma p by A sigma naught, del sigma p is the change in stress, normal stress, how the modified seismicity rate is different from the seismicity rate shown calculated by Dietrich in 94. The dashed lines represent the seismicity rate calculated by Dietrich for a similar situation, and the solid lines represent the seismicity rate by the modified Dietrich equation. So this new formulation we term it as a modified Dietrich formulation, and this black line over here is a Gaussian stress perturbation. So we see that Dietrich underestimates the seismicity by quite a significant margin. Hence the modified Dietrich does a much better job in forecasting seismicity. And also the Dietrich seismicity rate is only applicable if you do a step change in stresses. However, the modified Dietrich version by Jamieson and Siegel calculates seismicity rate due to a constantly varying stress with time. So based on this formulation, we will modify this a bit. So Jamieson and Siegel realized that the idea that all the faults are ready to go and all of them are above steady state is not true. In real life, some faults are dormant and some of them are ready to go based on the stress conditions over there. So they recalculated their formulation into something called a threshold rate and state in 2022, wherein they proposed that the seismicity rate now would be non-zero only when the system goes beyond the stress threshold. And the time it takes for a system to go beyond the stress threshold is T sub B, and otherwise the seismicity rate is just zero when time is less than T sub B. So the time for it to quote unquote go is the one which determines if a fault is going to go to instability, the instability or not. So over here, this delta S parameter is interesting. This delta S parameter is something called a Coulomb failure stress. So Coulomb failure stress shows or represents a potential for a fault to failure based on the shear and the normal stresses and the friction coefficient as shown by the equation below. Over here, delta S is equal to delta tau plus mu delta sigma. Delta S sub C is the threshold Coulomb failure stress, and a fault has to cross this threshold to fail. That was the idea proposed by Hamilton and Siegel. And this formulation is exactly what is useful to apply in a real life scenario for injection induced seismicity cases. So in this work by Hamilton and Siegel, they followed this workflow wherein the external stress evolution due to, let's say, tectonic loading or injection extraction changes the Coulomb stresses on the fault following this equation. Then we check if that Coulomb stress has crossed the stress threshold or not. If it has crossed the threshold, then fault has activated and is above steady state. Then nucleation happens following rate and state. Time-dependent nucleation, which is controlled by a sigma parameter and the T sub A, and then you get seismicity rate. However, if it is below stress threshold, then the seismicity rate is 0. You produce no seismicity. That's one of the assumptions of this work. So the problem over here is that the stress threshold term is a free parameter. So in order to actually find the stress threshold of a fault, you have to calibrate your seismicity rate with an actual seismicity rate observed out there in real life. If you calibrate it, you will get the delta SC parameter, and that will give you a representation of the critical stress criticality of the fault, if it is prone to earthquakes, nucleation or not. So the based on the final formulation of rate and state for friction for seismicity rate as proposed by Hymeson and Siegel in 2022 using the threshold rate and state formulation, we will solve a very basic problem to understand how that equation is being used to forecast induced seismicity. So for this, we will consider a reservoir of 2000 meter by 2000 meter arbitrary size, a 2D reservoir where an injection well is located right at the center. We impose a constant injection pressure of 1 megapascal over time. Over here, these units are arbitrary, so I'm just considering unit time, and the time range is 0 to 50 time units. We have 3 arbitrarily oriented faults as given by fault 1 and fault 2 and fault 3 on the right, and you can see all the details of the faults, the strike, dip, rake, the normal stress, friction coefficient, everything is mentioned over there. So the change in pressure at injection will change the Coulomb stresses on the fault. The change in Coulomb stresses on the fault will change the seismicity rate. So the condition imposed, the initial condition which imposed over here is that injection pressure just linearly changes with time as shown in the plot. So based on this condition, what's going to happen? So we can see over here, this is the evolution of pressure plume, and over here in reality you have to solve the diffusion equation with poroelastic modulation or no poroelastic modulation depending on your problem set. You have to solve it using a numerical method that could be finite differences or finite elements. That's the real way to go, but for the sake of saving time and simplicity and to actually focus the problem more towards the seismicity aspect of things instead of fluid mechanics or geomechanics, I assume that the evolution of the pressure field would follow a Gaussian as shown over here by this equation at the top. So you see F1, F2 and F3 are the 3 arbitrarily oriented faults, and we see that over time unit 49 from 0 to time 49.5 time units, how the pressure plume has evolved. You have progressively more and more and more pressure being developed in the region, which is affecting the Coulomb stresses on the faults as well. And this is what happens when you do a Coulomb stress analysis using the Coulomb failure stress formulation at the top given over there. So over here we see that the normal stress is changing due to the evolution of pore pressure, and normal stress, the change in normal stress is represented by alpha, which is the Biot's coefficient of pore elasticity, times the delta P, or the change in pore pressure. So we see that pore pressure at the folds are increasing as fluid diffuses, which results in normal stresses to fall down, as represented by alpha times delta P. Shear stress increases, and the Coulomb stresses also increase following the CFS formulation. Now we put the change in Coulomb stresses into the threshold rate and state seismicity rate equation, and we see that, and we also set a threshold time value at 10. And over here I have to remind one thing, that since we don't have an earthquake catalog to look at the actual seismicity rate, we cannot determine exactly what that stress threshold is. So we assume that all the Coulomb stress changes that we plot over here are above relative to the stress threshold. So we assume that the stress threshold has already been reached by the faults when this pressure diffusion situation is happening. So based on that, we put that into the threshold rate and state equation, and we see this very nice characteristic seismicity rate following an Omori decay for the 3 different faults. If you remember, this looks very similar to the Dietrich formulation in 1994, which is interesting, but instead of a step stress change, we are following a continuous time varying stress change over here, which is great. And the cumulative seismicity evolves gradually over time like this. So this problem gives you an insight into how we can, use the concept of rate and state friction in the context of induced seismicity and use it to forecast induced seismicity out there in the field. And it's a very, very efficient workflow, and we will see and actually in industry and in academia right now, researchers are using this workflow a lot to forecast induced seismicity in a variety of settings. It has been done for the Otaniami stimulation in Finland and bunch of other enhanced geothermal systems all around the world. It has been done to forecast induced seismicity in oil and gas fields in Groningen in Netherlands, and also in river raft geothermal field, which is a conventional geothermal field, and has been applied to a bunch of other places as well, and is very efficient and accurate in forecasting induced seismicity with very minimal physics and very minimal mathematical formulations, thanks to the simplification of Dietrich rate and state by Heimisen and Siegel in 2018 and 2022, which very easily helps us implement the concept of rate and state friction into a real one scenario where injection and extraction operations are changing the in situ stress conditions. And this is a very simplistic example of it, but nevertheless it gives us a very good idea of how we can use the rate and state formulation to understand earthquake nucleation mechanisms. So I will end this lecture with proposing this workflow over here, which was developed by my professor Dr. Matteo Acosta in his 2023 paper about earthquake nucleation. So they proposed a feedback loop wherein you get operations data, which are the pressure changes from wells, put it in the reservoir flow model where you solve the diffusion equation with your appropriate boundary conditions. Then the change in pressure with time and space is fed in the mechanical model, just like the Coulomb failure stress model as I showed before. Those changes the stress state in the fault. That changes seismicity based on the seismicity model. Then you do uncertainty quantification of it, and you do hindcasting or forecasting, and then you minimize the seismicity rate such that your Coulomb stresses are changed and your injection and extraction stresses are changed, so that your seismicity rate in the end is below a given threshold. And this is a mathematical theory of control that we are trying to impose for an n number of wells out there in the field to effectively control the earthquakes which are happening in real time, and effectively modify our injection extraction operations such that the seismicity rate does not go above beyond a certain threshold value and does not cause destruction. And it is a very, very effective model as demonstrated in the paper by Kim and colleagues in 2025, wherein they successfully implemented a mathematical theory of control-based optimization strategy for a single well injection stimulation scenario for an enhanced geothermal system in Otaniami in Finland. And my target is to expand that to an n number of wells, because if developed, this tool would be a game changer for the geothermal industry in general, wherein you can get maximum flow rates, maximum energy extraction, and minimum seismicity rates. And that is the overall target of our research, to effectively forecast, understand the physics behind earthquake mechanics, and also, since we're trying to understand the physics, we also would want to control the process of earthquakes and know what is causing those earthquakes, so that we can effectively modify our injection extraction operations to ensure that our potential for earthquake nucleation does not go beyond a certain value that could cause death and damage and destruction, which we would not want. Hence it's so crucial to understand the fundamentals and the physics behind earthquake mechanics. And there is a lot to be done as well. We have to conduct much more experiments to understand the characteristic A and B parameters, the exact physical meaning behind it, and constrain them. However, with time and with more and more technology available to us for conducting experiments, as well as numerical modeling, software packages, and advanced coding tools, we are able to get there gradually, step by step. But however, this mathematical theory of control system is now state of the art, and it has been effectively used in some of the geothermal scenarios out there, and works really well. And our plan is to expand on this. So with that, I want to end my lecture, and I hope it was very insightful. And it was a very mathematically heavy lecture, but unfortunately the entire field of earthquake mechanics is just like that, and I tried to make it as simple and easy to understand. And I would encourage everyone to go and learn a bit more about it, because it's a very interesting field, and I would be more than happy to have any kind of questions sent over to me by email or as a comment when I submit this video onto Canvas. I would be glad to answer any questions anyone has. With that, thank you so much, and have a good day.